Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at ArterisIP with Garibay, who's going to talk about what it takes to design a 7-nanometer chip and how those are different from previous nodes. So Ty, as we move into the 7-nanometer node, what changes? How much more difficult does this become?
Well, Ed, I think that's going to be a very significant change for people. The industry has moved from 28 to 20, 16, 14, or something like that. Some people have gone to 10 or 12, but many companies are actually skipping from 16 nanometer or 14 nanometer directly to 7. And there's going to be a very significant increase in the challenges, the normal everyday challenges, and then new challenges that are going to be unique to 7 nanometer. One of the things that we say at Arteris is that there will be no simple 7 nanometer chips. If you make the choice to take on the challenges of 7 nanometer, you're doing it because you have to. You feel that you need to get to that node to achieve some lower level of power consumption, some higher level of performance, or some massive level of integration to create a super chip, or mega chip as we're calling them, that brings together a tremendous amount of functionality. So the motivations that drive people to move to 7 nanometer inherently are pushing the limits. And this is normal for any given process, new to any given process node, but 7 nanometer then brings its own challenges.
Why don't you draw some of this out for us?
Sure.
So why don't we go through these one at a time? What are some of the big challenges?
So the biggest challenge of 7 nanometer is exactly what you'd expect from any new node, is the sheer amount of logic and functionality that you're able to put onto a chip in 7 nanometer. Even in existing process today, NVIDIA has stated that they put 21 billion transistors on their latest device, which is an 800 square millimeter chip. It's a monster by any measure, by every measure. So when we look at what will be possible in 7 nanometer, double, triple, maybe even quadruple that. We could approach 100 billion logic and memory transistors in a device in 7 nanometer. The capacity to imagine the architecture that fills that die, develop it, design it, verify it, and implement it all the way through to something which can be manufactured is the primary challenge in and of itself.
A big problem that people have been facing has been cost. On the cost of moving to even the first FinFET node, this gets even worse because this is the next full node change here.
Yes, definitely. So, and cost is clearly going to be one of those things that will hold people back. It's not clear that cost per device, cost per transistor, is actually going to get better going from 10 or 12 or 14 to 7. So you're having to add value in that product linearly with the increase in logic count. Whereas before we used to be able to say, okay, let's just make it smaller, it'll get cheaper. I can make basically the same functionality, slightly higher performance, lower power, and it'll be cheaper and everybody's happy. And that drives the business forward. But the cost today will come in 7 nanometer, will come in at least 3 different ways. There's the silicon cost, which certainly is a challenge. There's a design cost, which is going to be huge. Again, simply because there is the complexity, the possibility of having a huge number of different functions. But then the cost of realizing those functions into polygons is going to be huge. The rules keep getting more and more difficult to meet at the layout level. In 7 and 10 nanometer, or in 10 nanometer and 12 nanometer today, we're already seeing triple patterning requirements for all the finer metal layers and the base layers. In 7 nanometer, the expectation is that would go to quadruple patterning, that many more metal steps, or that many more mask steps in the process, incremental cost just for the masks themselves, which could easily go to $10 million or more per mask set. That many more steps, increasing the time in the fab, which is already 6 months, could go to 9 months. It could take almost a year to build a 7 nanometer device. Samsung has claimed they're going to go to EUV, which would be a first for the industry, and probably brings its own set of challenges. Although it may simplify the layout itself, the cost of deploying EUV in volume is again going to reflect down to the cost of the silicon.
So which markets do you see actually driving this?
Big markets, and big markets that allow for relatively expensive parts. And pretty obviously there's at least 3 that are going to meet the needs or meet those requirements. One is data center. So what we'll see is a continued push by the big players that are already there, Intel, others, to continue to push into getting more and more computes onto a die at higher performance and lower power. But what we'll see is a whole raft, dozens of new players trying to get into data center with AI chips based on new architectures that are purpose-built, targeted at dealing with the mathematics of convolutional neural networks and to support deep learning. So those chips, if the architectures are built right, if they are able to be fed by memory, can be made almost arbitrarily large, because the whole point is to pack on as much processing as possible and maximize the utilization of all the processing on a chip. The next market I think that is going to be significant for 7 nanometer is automotive. For autonomous vehicles, the amount of computation required is massive, especially as we bring together all the different disparate chips that are currently scattered around a car into a central car controller, plus add on the artificial intelligence processing necessary for autonomous. And the last market would be the normal one, which would be mobile. And there's always a push for lower power and higher performance.
As we move into markets like AI and some of the data centers, are the people building the chips the ones who have built these in the past, and do they understand all the complexity here?
We see that, especially as an IP vendor, we see that daily, that there's a huge number of new players entering the market. Many of them are very smart. They really understand neural networks, deep learning, artificial intelligence. But no, they've never really built chips before. And so there's a huge premium being put on senior chip development talent moving from company to company and starting new teams worldwide. Especially we're starting to see a lot of activity in China, where new teams are popping up almost daily, literally, that are attacking the AI market, AI technology in different markets, I would say. Everything from data center to automotive to wearables, all with an AI bent. And these new teams don't really understand the challenges that they're going to face in 7 nanometer. And so there's, I think, a significant market there for the infrastructure parts of our industry and tools, IP, services to support these teams to help them be successful in the market.
So this is sort of like selling shovels in the gold rush, right?
Yes, that's a very good analogy. The infrastructure companies look to benefit after a period of time where there's a lot of consolidation in the industry. And so there was actually fewer and fewer companies that were able to build at the more and more advanced nodes. And so it looked like that maybe the market was shrinking. But now with all these new players coming into the market and driving more unique design starts at more unique companies, there does look to be opportunities to provide solutions to more companies over time than we had foreseen perhaps a year or two ago.
And one of the shifts here is that it's not just what's going on inside the data center, it's now moving out into the edge nodes as well with some of the most advanced designs here, right? So now we have all the problems that we had in the mobile market, plus we have this massive amount of data that has to be moved through.
Yes, and so again, if you're going to go to 7 nanometer, it's because you want to achieve a certain goal. Often that is to have very high performance data processing. It means you have to have high bandwidth data in, data out, and data movement and processing on the chip itself. This was normal in data centers, in the telecom backbone, and that's going to continue. We're going to see 400 gig, 1 terabit type backbone communications. But now with 5G radios coming on board, at the edge you'll see normal transmit speeds of 100 megabits per second up to a gigabit. When you have thousands, hundreds of thousands, millions of nodes at the edge transmitting at that rate, what does that mean for the aggregation points that are having to bring all that together to run it back to cloud services? The long-term response is to push a lot of this processing out to the edge, to the security cameras, to the wearables, to the mobile phones, to the cars, which are probably going to be the most biggest generators of both data back to the clouds and also of processing data local to themselves. Every car has a huge number of sensors, sonar, LiDAR, radar, video, that they all have to combine and process in real time, obviously. Not all of that data can be shipped back, but the important data has to be shipped back. Maybe not in real time, but at least in a fashion that would make it usable.
And one of the big differences here is that, unlike in the past when a lot of these functions were off most of the time, what you're talking about here is fairly heavy usage on an almost constant basis. You think about a camera in a car, for example, which probably won't be at 7 nanometers, but the amount of data that's going to be drawing in will be almost streaming video. Other devices will be dealing with these kinds of sensory inputs at that kind of level too. What does that do to the design at 7 nanometers? You've got to move this data much faster.
Well, much faster, and I think, as you're pointing out, much higher utilization over lifetime. One of the projections that I've seen is that as we move more and more towards autonomous vehicles, it is likely that autonomous vehicles will see almost 24-hour use in an Uber type environment where people are owning fewer and fewer cars and they're using an externally provided autonomous vehicle. So that car, whereas we use our cars maybe an hour, maybe 2 hours a day, a autonomous vehicle in a fleet service could be seeing 20 to 24-hour use. That's then especially showing up in all their data feeds. So yes, the sonar cameras, the LiDAR probably won't be in 7 nanometer, although we've seen some companies looking at that. But the processing element the processing elements that are processing the data coming from those sensors that are also having to work almost 24 hours a day are going to be on all the time.
So now you've got dynamic power density, you've got a growing amount of leakage at each new node. 7 nanometers starts the whole cycle all over again versus what happened where we got a reset at 14, 16. You've got aging effects and electrical overstress. All this has to be calculated into the design and built into there, and now you need to start thinking about how long is this going to last and how do I design this? This becomes a lot more complex on those sides, right?
It does, and especially in the automobile where you have to meet functional safety and reliability requirements that are unique to those safety critical applications. And in many cases, design teams have not really experienced these. Design teams that are coming into this space have not experienced dealing with those requirements. And so we're having to figure out how to quantify what are the impacts of running at very high temperature, automotive spec range of 125 up to maybe 150 if you're sitting right on the engine. What are what's the possible aging effects? Even in 10 nanometer, we were seeing that the potential range of aging differences between devices was so large that if you actually tried to cover for them in margining, you were leaving a huge amount of time zero performance on the table. So how do we deal with that I believe we're going to have to figure out how to deal with that in an architectural way. To understand that the performance of these devices can change, but then make sure that there is a lower bound for real-time safety critical applications that can never be violated, or if it is violated, it's signaled as an error to the system.
Does packaging, advanced packaging of one sort or another help this, or does it just add another layer of complication?
So I think the real possibilities here are that 7 nanometer, and especially looking further ahead to 5 nanometer, these chips are going to be so difficult to build and so expensive to manufacture that it won't make sense to create a full system on a chip anymore. So what we've called a SoC, a system on a chip, may disaggregate again and start to look more like what we had in the 80s and 90s, where there was a super high performance CPU chip, and then you had a board of support elements, communications, I/O, memory, storage, all that kind of stuff. And I can see that replaying in starting in 7 nanometer and then accelerating to 5 nanometer, where we might have active substrate chips in 16 nanometer or 28 nanometer that have that are much more friendly to analog, that are capable of dealing with 100 gigabit SerDes, that allow flash, that allow different analog functions that are very difficult to build in the most advanced processing nodes. Put all that onto a base die and then build much smaller compute element chips that can be flipped onto that active substrate and connected through bumps.
There's been a whole push toward system in package, toward chiplets, toward 2.5D. All these apply?
Yes, so 2.5D system in package is to me more of a cost optimization. 2.5D is the first step towards this type of integration that I'm describing, because in 2.5D, although you're not flipping them the chips, you're bringing them edge to edge and putting the communication between them. You are allowing for each chip to have a different process node, and for the logic that is most optimal for that process node to be built in that technology. And so you're not trying to stretch a technology to cover all possible requirements of a system. And we're starting to see more and more companies take advantage of that, simply because it makes designs that might otherwise be almost impossible. It's still expensive, it still adds cost, but it can make a product something that you can get to the market now, as opposed to working another year or two to try to figure out how to solve these problems all in one node.
You control the fabric in between those chips and between the IP that goes into those chips. Does that change significantly as you start moving into these different architectures? Do you get more freedom? You have a little bit more leeway on the characterization than what you had in the past?
I don't think we get any more freedom. I think it actually just gets harder and harder. The performance requirements just keep going up. At 7 nanometer and 5 nanometer, the cost of every square micron of silicon is simply higher. So the burden on all parts of the design is to dramatically optimize the total wire count, the total device count. But the wires aren't getting any faster, right? So transistors, yes, you're locally, local communication and local operations are getting higher performance, but trying to cross a chip is pretty much stuck where it's been for the last couple of nodes. So there's a huge benefit potentially to people who can create architectures that understand these challenges, optimize the interconnect both on chip and off chip, to build the inherent delays into the architectures and take advantage of them if possible, at least account for them.
So in that type of scenario, the 7 nanometer logic would probably be almost a platform for the digital logic there, right? And everything else would be changed around it?
Yes, and I think that's almost an optimal design approach, because it allows the high performance designers to focus their efforts on the real high value added pieces of logic. This is the part that's going to crunch the data. All the other stuff shouldn't change that frequently. What we're seeing today is a generational change of moving from DDR4 or standard off-chip memories to maybe HBM2 attached memories, or even DDR5 or GDDR6 type memories. But once we make that change, that's probably good for a while, and those interfaces are what you're going to have, and you could live with that over for at least a couple of years, maybe 2 generations.
Ty Garibay, thanks for a great explanation of what's coming.
Thank you very much.